You ever stop and wonder what's really happening? I mean, deep down inside a computer chip. Forget all the software, forget the operating system for a minute. We're going to go way down to the metal, to the physical level. We're talking about the elegant, powerful, and honestly fundamental principles of what's called transistor logic, or TTL. All right, let's get right into it. I mean, think about it. Everything from the phone in your pocket to the most powerful supercomputer, it's all built on literally billions of tiny switches, all performing simple logical operations. And deep inside those incredibly complex circuits, it's not magic. Not at all. It's just brilliant, simple engineering. And it all started with circuits just like the ones we're about to break down.
And that really brings us to the core question here. See, before we had these neat little integrated circuits with pre-made logic gates, engineers had to build them from scratch, right? From the ground up. So how on earth do you take a handful of simple transistors and actually make them think? Well, the answer is TTL.
All right, so let's check out the blueprint and see how this all works. You'll see that every standard TTL gate follows this really consistent and, well, logical structure.
So what exactly is transistor logic? Well, it's a classic family of digital logic where every single piece doing the thinking, the inputs, the processing, the output, is literally a transistor. Just transistors. And this all-transistor approach, man, it was a total game changer. It really did pave the way for the digital age.
Okay, let's break it down. A typical TTL circuit is built in three main parts. First, you've got the input stage. That's what grabs the signals. Then there's a phase splitter, which kind of processes that input. And finally, the output stage, which, you guessed it, delivers the final result.
And here it is. This is that blueprint in action. We're looking at a classic TTL NAND gate circuit. See Q1 over there? That's our input stage. Q2 in the middle is the phase splitter, and then Q3 is our output stage. So let's start at the beginning and take a closer look at that input.
Okay, the real secret weapon of TTL is this thing right here, a multi-emitter transistor. It's kind of like having multiple input diodes all mashed into one super efficient component. And here's the clever part. If any one of those inputs goes low, this transistor immediately yanks the current away, basically starving the next transistor Q2 and forcing it to shut down. It's an incredibly smart design, like a bouncer at a club.
All right, so after the input and the phase splitter, we get to the output stage. The logic has been processed, so how do you actually send the signal out? Well, it turns out there's more than one way to do it. It's almost like a design debate, with three big contenders, and each one has its own unique philosophy.
First up, we've got contender number one, the open collector. This is kind of the minimalist approach. It's simple, for sure, but there's a catch. So with an open collector, the gate is really good at one thing, actively pulling the output low, connecting it straight to ground. But what about creating a high signal? Well, it doesn't. It does literally nothing. The output just floats there, disconnected. It's up to you, the person designing the circuit, to add an external pull-up resistor to actually define what high means. It's flexible, yeah, but it means a bit more work for you.
Okay. Next up is the fan favorite, pretty much the heavyweight champion of TTL outputs. This is the one you're going to see most often, the totem pole. The totem pole is all about performance. We're talking speed and power. It uses two transistors stacked right on top of each other, just like, well, a totem pole. The top transistor's job is to actively pull the output high. The bottom one's job is to actively pull it low. They work as a perfect team, always in opposition, making sure you get a strong, fast, and super clear signal every single time.
And finally, that brings us to our third contender. This one is the specialist, designed for a very specific but very important job. It's called the tri-state output.
So a tri-state output basically takes that totem pole design we just saw and adds a little magic trick, an enable pin. When that pin is disabled, the output doesn't go high and it doesn't go low. Instead, it enters a third state called high impedance or high Z. In this state, it pretty much just disconnects itself from the circuit entirely. It's like it's not even there. And this is absolutely crucial for things like a computer bus, where you have a bunch of different devices all trying to talk on the same wire.
Okay, but let's circle back to our most popular design, the totem pole, because for all its strengths, the original design had a really serious hidden flaw. I'm talking about a design drama that could literally fry the chip.
So take a look at this circuit.
I mean, on the surface, it looks perfectly fine, right? You've got Q3 up top, the pull-up transistor, and Q4 on the bottom, the pull-down. And in theory, one should be on while the other is off. But there's this tiny, tiny window of time right when it's switching where things can go catastrophically wrong.
So here's the million-dollar question. What happens if the inputs switch in just such a way that both Q3 and Q4 are turned on at the exact same time, even for just a split second? The answer is not good. You basically create a direct path from your power supply, VCC, straight down to ground. That's a dead short.
And this is the absolute #1 rule. The source material is super clear on this. In totem pole configuration, Q3 and Q4 must never be on together. You just can't have that. This condition is called shoot-through, and it creates this huge spike of current that can overheat and totally destroy the transistors. It's a critical failure just waiting to happen, hiding inside this otherwise clever design.
But check this out. Here's the solution, and it's brilliant. On the left, you see the flawed design, and on the right, the fix. And what was the fix? Just one tiny little component, a single diode, placed right there. All this diode does is raise the voltage needed to turn on that top transistor Q3 just a tiny bit. But that's enough to give Q4 time to turn off completely before Q3 even has a chance to turn on. It's such a simple, elegant solution to a really critical problem.
Okay, so we've looked at the building blocks, we've even fixed a major flaw. Now for the payoff. How do these arrangements of transistors actually become the logic gates that, power our entire digital world?
Remember that corrected totem pole circuit we just fixed? Well, guess what? That whole thing is a NAND gate. If you look at the truth table, you'll see the output is only low when both input A and input B are high. That physical arrangement of transistors, it perfectly creates that abstract logical function. Pretty cool, right?
So what if you need an AND gate instead? Easy. You just build on what you've already got. You take the output from your NAND gate and just pop it through a simple inverter. A NAND followed by an inverter, that gives you an AND gate. It really is like building with digital Legos.
And we can keep going. If we just rearrange the transistors a bit, putting them in parallel instead of in series, boom, we've got a NOR gate. And with a NOR gate, the output is low if either input A or input B is high. So with just these few basic configurations, you literally have the complete toolkit. You can build any digital logic circuit you can dream of.
The engineering behind these old TTL gates is it's so elegant. But it really makes you think, doesn't it? If it took such a clever little fix to solve a timing flaw with just a few transistors back in the day, what kind of mind-bending dilemmas and hidden dramas are today's chip designers solving? Not with a handful of transistors, but with billions of them, all packed onto the tiny chips that run our lives.